the screen only hangs out down below. So this is your tuition money at work, right? And do people still use overhead projectors? This is like the 1930s. Anyway, for those of you who weren't paying attention, I am not Lawford. Yeah, I know that's a real surprise, right? Lawford is not here today, so I'm pinch hitting. My name is Paul. I'm another professor in the neurosciences department. And forgive any rough edges because, again, I'm not Lawford, and I know Lawford's a hard act to follow. So be patient with me. So as I understand it, the topic for today's lecture is supposed to be, you guys have been talking about climate change, right? Your last lecture was about climate change, more or less. Some sort of general consensus here? What was the last lecture about? More or less climate change. Okay, good enough. So what we're going to talk about, and I think my understanding is what you talked about last time was sort of climate change in a modern context, right? Global climate change that's going on now, atmospheric pollution, greenhouse gases, that sort of thing. What we're going to look at today is climate change not in the present, but, well, it is in the present, but also going into the past. We don't understand, when you're projecting forward, you want to understand how things are changing now and how things are going to be in the future. As a scientist, you want to perform an experiment, right? And say, well, what happens if we change carbon dioxide concentrations on Earth's surface? What if we doubled them or tripled them? What's that going to take us? Where's that going to take us? Unfortunately, we don't have another planet on which to experiment, and we don't have a time scale for that to happen. So the best way to understand it is to look, instead of trying to perform an experiment to move into the future, to look into the past and say, well, how much has climate changed in the past, and what were the conditions like? Did you have, was carbon dioxide higher than today, lower than today? What were temperatures like as a result? Did you have glaciers? Did you have an ice age? Did you have a torrid age where it was really hot? And what were those conditions like? And can we then take that and apply that to the future? So, looking at the past, just over the past 2 million years, okay, a period known as the Pleistocene epoch, Pleistocene right here. There is evidence in the Pleistocene, from over the last 2 million years, that average temperature on the Earth's surface has fluctuated wildly, plus or minus 10 degrees Celsius relative to what it is today. Okay, so there were times in the past, so if you go back roughly 18,000 years ago so to the peak of the last ice age, global temperatures were about 10 degrees Celsius cooler than they were today. That's a hell of a lot of temperature. That's cold. Okay, but then as you go back in time, again, this is all, and this is sort of I don't know how much actual data is in this plot, but it's a cartoon figure that's compiled out of a lot of different data. So that's back 16,000 years ago, so here we are today. If you go back even further, about 100,000 years ago, to the last interglacial period, which is what we're in now, you see temperatures were like 6 to 7 degrees Celsius hotter than they are today. So we know that in the past, in the recent past, just over the last few 100,000 years, you've had temperature swings plus or minus 10 degrees. There's a lot. And what kind of temperature change were you talking about with global warming in your last lecture? Like what are the projections for the next 100 years? How much climate is going to change? How much global average temperature is going to change? Lawford talked about that at all? No? Okay. You're talking, somewhere between 1 and 5 degrees Celsius, okay, over the next 100 years, based on the latest IPCC climate assessments. So, that sounds like a lot, but it's actually not a lot when you put it in the context of how much climate's changed naturally. Obviously, a few 100,000 years ago, there was no anthropogenic forcing on the climate system. You didn't have factories spewing carbon dioxide into the atmosphere, or methane into the atmosphere. So this is just natural variability within the climate system. You can have huge swings, okay? So what we're going to talk about in particular, we'll go back to this for a second. These periods, the last 2 million years, we've had a series of very cold periods. Depending on who you talk to, between 16 and 20 of these periods, we had extremely cold temperatures, and then periods of warm, where you're 5 or 10 degrees Celsius above modern conditions. These periods of extremely cold were periods that are known as glacial periods. You had extensive glaciers covering the northern hemisphere, mostly the northern hemisphere, but also some of the southern hemisphere, and the glaciers were growing or advancing, covering large amounts of the continents. Okay? So there were, again, roughly from 16 to 20 of those over the last 2 million years. So roughly every 100,000 years or so, you get glaciers start coming in, creeping and creeping and creeping in, and temperatures get really cold. And then in between these periods, these little tiny periods where you're actually warmer than average, these are what are known as interglacial periods. Typically, 100,000 year cycle between glacial events, most of that period is dominated by the glaciers. Most of that time is cold. 40 to 80,000 years of that or so is cold period, extremely cold. And then these interglacial periods, the little warm periods, like the period that we're in now, we're coming out of the last glaciation, we're on our way into one of these interglacials. Those are extremely brief, relatively speaking, maybe 10 to 20,000 years of warm separated by 40 to 80,000 years of cold on average, okay? So this entire period is what's known as the Pleistocene Ice Age, the idea that we've had these repeated glaciations and interglacial periods, cycles over the last 2 million years. That whole period is known as is an ice age, and within that you have glacial periods and interglacial periods. Now, who came up with the idea of the ice age? The idea of the ice age, a global sort of period of extended glaciation on the continents, first came about in 1836 from this guy, Louis Agassiz, who was a Swiss geologist, and he was interested in trying to understand, has anybody here been to the Alps? So when you go into the Alps, there are lots of, it's beautiful country, but as you go up into the mountains, there are these random big blocks of boulders just sitting in the middle of valleys, right at the bottom of valleys. And it was a real problem in the early 19th century for geologists trying to explain how you get this massive boulder sitting in the middle of a valley, far removed from the edges. It's too big, people didn't pick it up and move it, right? And a little tiny stream trickling by, how did it get down? And you see that actually around here too, in the Boston area, and in Massachusetts in general. You have these large boulders sitting out in the middle of the fields, and you think, well, how did that get there? That doesn't look right, okay? So Agassiz actually developed a theory that said that what happened was these boulders were transported by ice, okay? Because there were glaciers in the Alps, up in the valleys, in the northern parts of the valleys. They just weren't down at the bottom. So you can go out on the glaciers and you can see that they're giant boulders that are stuck in the glaciers, and the glaciers move a little bit and move the boulder along with them. And the idea was, Agassiz's idea was that there was a time in Earth's history when temperatures were much colder. Because they were much colder, the glaciers extended much further down the mountains. With them, they had these boulders that they picked up from further up in the mountain. And then, at some point in Earth's past, temperatures warmed up. As they warmed up, the glaciers retreated and left the boulders behind. Okay? That was the observation there. And he proposed it in 1836. He actually scooped one of his buddies. He wrote a book about it for his buddy who had actually come up with the idea could write the book. It caused some hard feelings. But it also got him a job at Harvard. So he was a professor over at Harvard in the Earth Sciences Department. Well, then was the geology department, but it's now the Earth Sciences Department. There's a building name for him over there. And he's actually buried just across the river in Mount Auburn Cemetery over in Cambridge. So you can go over and visit him and pay homage to him. I think there's a middle school, an elementary school in Cambridge, the Agassiz School. It's named after him. So he was the first guy to really look at this idea of the Ice Age. He subsequently, in 1840, went to Scotland, and in the Highlands of northern Scotland, he discovered similar features in the mountains there. And that led him to go from, well, it wasn't just a local phenomenon. The ice sheets weren't just local to the Alps. They were actually global, because you have the same features in another part of the world, in this case Scotland. And he proposed one big large ice sheet covering the Earth at some point in the Earth's past. At that point, they didn't know how far in the Earth's past, but that was the basic idea. Okay. So, how do we know? How do we know that we have glaciers in the past? How do we know that temperatures have changed in the past? It's really simple. Over the last 150 years or so, you can go back. How would you, if you wanted to know how much temperatures have changed over the last 150 years, or how about over the last 10 years, what would you do? Is there any place you could go for information about temperatures? What's that? Ice cores? That's a little, that's going after a fly with a sledgehammer, but yeah. Yeah.
The last 10 years.
Yes, the internet. And what does the internet tell you? They have everything on the internet. That's great. In particular, you could go to like the National Weather Service, right? And the National Weather Service, they have all sorts of information online, data, right? What kind of data would they have that would be useful? Temperatures. And where do they get their temperatures? Using thermometers. Yes, that was a lot of ground to cover to get the thermometer. So the point is that over the last 150 years, we have actually recorded temperature on the surface of the Earth with thermometers. We've gotten better and better coverage as time has gone on, but there are reliable instruments, instrument records. You can go back and people have been recording temperature at observatories back over the last 150 years or so. So over the last 150 years, we have relatively reliable data on what temperatures were like on the surface of the Earth. And using that, you can reconstruct, this is, relative to, oh gosh, what is this? This is relative to 2000, the year 2000, is that right? No, 1980. This one's referenced to 1980. Okay, so you can see that this is temperature anomaly on this side. So it's how much did the temperature, how much was the average surface temperature of the Earth different from the average surface temperature in 1980? So if in 1980 the average temperature was 17 degrees, that would mean that in 1860 it was, 16.5 degrees. Okay? And it also means that in 2000 it would be 17 plus 0.4, so 17.4 degrees. Yeah, I know, it's hard math, but I don't have a calculator up here, give me a break. So you can see that over the last 150 years, we have pretty convincing evidence. If you believe thermometers, if you believe in a thermometer, yes, people are already starting to jump ship. No. I'm not Lawford, I can't help you. Okay, if you believe thermometers, then you can't help but conclude that over the last 150 years, the Earth's surface is warmed by about 1 degree Celsius. If you believe thermometers, that's just the data. There's no arguing with that. So if you wanted to go back further than 150 years, before you had thermometers, what could you look at? How would you get data? Yeah?
You can look at ocean sediment cores.
You can look at ocean sediments. Okay, that's one way to do it. In an indirect way. There are problems with ocean sediments. Any other way?
Using glaciers.
You could look at what?
Glaciers, like the properties like glaciers.
So you could look at glaciers, in particular you could look at ice cores, right? Cores of ice that actually contain annual records, because every year you get these sort of annual rings that form. It's just kind of like tree rings. Another way you could look at it is tree rings, right? So you could look at tree growth records and that sort of thing. We know what conditions, under what conditions in terms of temperature and humidity, trees grow well and trees grow not well, and you can use that to actually reconstruct climate records. And that's what people have done. So today, right now, this is deviation. You probably saw this last week. Deviation in temperature from the mean currently over the last 10 years, over this 10-year period. We've got warming going up here, warming going on here, cooling in Antarctica, cooling in the North Pacific. Going back over the last 2,000 years, sorry, the slide's a little out of place. Going back over the last 2,000 years, this is constructed using a variety of methods, largely using things like tree rings, dendrochronology. You can construct global temperatures, a global temperature record going back over the last so here's today, here's going back over time, and you can see, again, this one is referenced to the year 2000. So 0 is the year 2000, and these are all plus or minus temperature relative to the mean in the year 2000. But you can see that over the last 2,000 years, you've gone through some variation, both long-scale variations. So you had a period of relatively low temperatures in the 1600s and 1700s, a period known as the Little Ice Age. And then you had a period of relatively warm temperatures from about 1,000 to 1,200, known as the Medieval Warm Period. And before that, temperatures decreased. Superimposed on that, so that's the large-scale feature here. Superimposed on that, you've got a lot of high-frequency noise, so rapid variations from over, decadal, annual to decadal sort of time scales, and those variations can be on the order of 0.5 degree Celsius or so. So there's a lot of variability in global temperature. Going back even further, as some people said, actually as you said, you could go, if you wanted to go back further than the last 2,000 years, you can start looking at things like ice core records. So glaciers, when you have glaciers like you have in Greenland or you have in Antarctica, they record, every year you're accumulating more and more snow. And there's a seasonal cycle to the snow. You can actually see, if you look at, over time, the snow layers compressing, and they actually form little discrete layers, kind of like tree rings in the ice. So you drill a core out of the ice, pull it out, and then you can look and you can just count back through the seasons of snow. You can count back and see discrete layers. And then within that discrete layer, you can analyze things like oxygen isotopes, which are a proxy for temperature. Have you guys talked about oxygen isotope records at all? You all look shocked. I see a deer, at least one deer in the headlights. Okay. All right. You don't need to worry about it too much, other than the fact that you should know that their oxygen, which sits over here on the periodic table, has a couple of useful isotopes. So one isotope has 8 protons and 8 neutrons, and that's called oxygen-16. The other isotope has, or one other isotope that's useful, has 8 protons and 10 neutrons, so it's called oxygen-18. Okay? Oxygen-16 evaporates more quickly. Water with oxygen-16 molecules in it evaporates more readily than water with oxygen-18 molecules in it. So as temperature varies, the ratio of oxygen-16 to oxygen-18 in the world's oceans change. And you can actually measure that in marine sediments, and you can measure it in the snowfall that results from water evaporating off the oceans and then snowing on land. Okay, that isotope, the variation in the isotopes is actually preserved in the ice record. Okay? So doing that, you can go to places like Vostok. Vostok is a giant ice core. Well, Vostok, Epica, this is from Antarctica. Vostok's from Antarctica, I think. Yeah, Vostok's from Vostok Station in Antarctica. And these are ice records going back over the last 450,000 years. This is change in temperature using a scale. So the idea is that you measure the ratio of the isotopes of oxygen, and then you relate that to a deviation in temperature from the current situation, the current conditions. Okay? Again, it's what's called a proxy record. You're not measuring temperature directly, you're measuring something that depends on temperature, and then using its dependence on temperature to predict temperature. Okay? And then going back over time, you can see that here we are today, and we're relatively warm, and then you go back just 15,000 years ago, and suddenly we're 7 or 8 degrees below Celsius, or below modern temperatures in terms of Celsius. And then you go back, and it's a long period of relatively low temperatures, and then here we are, high temperature here, low, 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 high, low, high, low, high. And that's confirmed in Epica. This is an ice core from a station in Antarctica. Vostok is an ice core in Antarctica. This is just ice volumes, just shows that it correlates. The idea here is that what you're seeing are these brief interglacial periods in the temperature, and then the long periods of glaciation in between. So glaciers, no glaciers, glaciers, no glaciers, glaciers, no glaciers, glaciers, no glaciers. Got it? And you get this just from looking at ice. Now the problem is that our ice cores don't go back very far. The ice cores only go back roughly about 800,000 years. Okay? The ones that we've recovered at least. In theory, you could go back further than that, a little bit at least. But so we're limited to 800,000 years. If you want to go back further than that, the way to go is with ocean sediments. Ocean sediments, again, preserve the oxygen isotope record of the ocean water that they're formed in. So you have little critters floating around in the ocean. They're soaking up oxygen, using it to make their shells. When they die, they float down to the bottom of the ocean, create a sediment layer, and preserve that oxygen isotope record in their skeleton. So if you dig up the dirt at the bottom of the ocean, the sediment at the bottom of the ocean, same sort of process you can look at in terms of depth within a core of sediment. You can look at how the oxygen isotope record varies, and again, relate that to temperature, because you know how oxygen isotopes vary with temperature in the modern world. Okay? And doing that, you can go back millions of years to hundreds of millions of years. Okay? So here, again, here's the Pleistocene, the last 2 million years. You can see that these periods of, over here, this is the Del 018 record, so this is the oxygen isotope record over here, in terms of deviation from the norm. Over here it is converted to temperature, the value converted to temperature, and you can see that you've got large variations, big variations in temperature, going back over the last 2 million years, and each one of these big swings corresponds to a interglacial cycle. You go back before 2 million years ago, there's one other thing that comes out of this record when you look at it. What were the temperatures like 2 million years ago, and before 2 million years ago, actually? Have temperatures overall been increasing or decreasing? So this is 5 million years ago. This is today. Have temperatures on average increased or decreased over the last 5 million years? They've decreased. Temperatures have been going down. And they really started going down about 2.5 million years ago. And that's when we entered the Pleistocene epoch and we had started these glaciations. Global temperatures have been cooler over the last 2.5 million years than they were before that. Going back even further, so this is the portion of the record that we just saw was right here, right, the Pleistocene. and a little bit of the Pliocene. So the 5 million years. You can go back even further and extend that sediment record back. And what you can see is that, again, this is Delo 18. This is temperature on this side, on this axis. And you've got periods of low temperature over here. So globally, you go back 50 million years ago, and temperatures were actually about 10 degrees Celsius higher than they are today. Okay? So temperatures have been very high prior to this, and there's been a gradual decrease in temperature at the surface of the Earth. You can go back even further than that, and before this, in the age of dinosaurs, temperatures were even hotter. There are a number of reasons for this, mostly related to plate tectonics, seafloor spreading rates and volcanism and all of that. And then at the end of the Cretaceous period, death of the dinosaurs, you had a big meteorite impact that instigated a cooling effect. The cooling effect has been playing out ever since through a variety of mechanisms. Going back even further, over the last 500 million years, what's known as the Phanerozoic period. Here we are today. This is 540 million years ago. This is, again, looking at oxygen-18 records from sediments, not all of them seafloor sediments, but from other places. And you can see that you've gone from periods, you have periods where temperatures are much hotter than average, and periods where temperatures are much colder than average. And in particular, over the last 500 million years, there have been 4 distinct periods of glaciation. Four points in time, from the Pleistocene year, Cretaceous, the Permian, and the Ordovician, where you've had major ice ages. So you've had extensive ice sheets covering the northern hemisphere, okay? Part of the southern hemisphere. So again, temperatures have varied wildly over the Earth's history, and we've had a number of periods where you've had extensive, and these have lasted for millions of years, tens of millions of years, these periods where you have glaciers, then no glaciers, then glaciers, then no glaciers. Before this, there was a very special glaciation that happened. There's evidence for a very special glaciation that happened about 800 million years ago during a period known as the Cryogenian. During this period, it's actually believed, and this is before complex multicellular life arrived on Earth. But there's evidence here that 800 million years ago, the entire surface of the Earth was covered in ice. It wasn't just glaciers around the northern hemisphere like we had during the Pleistocene glaciations, where they'd come down to 35 degrees latitude and then retreat. We're talking ice at the equator 800 million years ago. And for a period of roughly 100 million years, the entire planet was just encased in ice. Okay? We have evidence for this in the form of glacial deposits, the evidence of past glacial at a range of latitudes from this time. So you can look at continents that were located at the equator, you can look at continents that were located at high latitude at this time, and all of them have extensive evidence of glaciation, extensive glacial deposits. So again, the geologic record tells you that there was a period of time, roughly 100 million years ago, roughly 800 million years ago, it lasted for roughly 100 million years, where the entire planet was probably encased in ice. Okay? Interesting point is that after this ended, after this period ended, because one question is how do you actually get out of that situation? But after this period ended, it was almost immediately afterwards followed by the what's called the Cambrian explosion, which is when life went to taking on multicellular form with hard shells and that sort of thing. So life as we understand it, things other than little unicellular organisms floating around in the ocean, very simple cellular organisms floating around in the ocean, really took off after all of the snow melted. So, and there's some theories that the two are obviously related. The warming after this created a climate that was appropriate for the rise of complex life. Okay, so how do you get ice ages? Any ideas? How do you? And let's not say ice ages, because ice ages is sort of colloquialism. How do you get glaciation?
Well, doesn't the slow have like certain oceanic currents?
It can. So most of the, well, a huge part of the Earth's heat budget is dominated by the oceans taking warm water from the equator and moving it to the poles. If you can block the flow of that water, then you change the way heat is distributed on the surface of the Earth. And as a consequence, you can get glaciation. Okay? You can in certain areas. That's kind of what's going on here. In this case, plate tectonics, the way you change the ocean currents at that scale is often in terms of, or for extended period of times, is you move the continents around in plate tectonics. And one way to do that is to put one way to block this northwest transport or minimize the impact of north-south transport is to put continents on the poles. In this case, Antarctica is sitting on the pole. Okay, so Antarctica is sitting on the pole. What happens to Antarctica? The water can no longer make its way all the way down to the pole because it hits a continent before it gets there. You end up getting really cold at the pole, right? Because you're getting really cold, you get snow. As you get snow, it accumulates on the land. What happens? Did you guys talk about albedo last time?
No.
Okay, albedo is the reflectivity of the Earth's surface. Okay, it's like this. You all know this one, right? Are you hotter on a summer day wearing a dark shirt or a light shirt? A white shirt or a black shirt? Black shirt. Okay, because the black absorbs more energy from the sun, right? Whereas the white reflects it. Okay, so if you take ground here, land surface that's mostly dark, and cover it with nice white snow, what's going to happen to the temperatures? Is it going to be cooler or warmer? Cooler, because you're reflecting more of the light. You're not absorbing it into the ground, you're reflecting it back off into space. That's called albedo. Albedo is the amount of, how much of radiation hitting the ground, hitting the Earth is reflected back out into space. So as you convert this land mass, cover it with snow, make it white, white increases reflectivity, less of the radiation from the sun is absorbed. That drops temperatures. What happens when you drop temperatures? You get more snow. Snow sticks around longer. So you get more snow, you reflect more radiation, temperatures drop more. You get more snow, you reflect radiation, temperatures drop more, you get more snow. You get the idea, it's a positive feedback loop. Okay? So sticking a continent on the base of the, right in a polar region will do that. Will actually instigate an ice age. And you get local ice sheets forming, at least, on Antarctica because of that. Okay? Stick a continent in the pole and you're going to get ice sheets forming. The two prominent examples of that today are, of course, Antarctica and Greenland. Greenland, of course, being near the North Pole. The North Pole itself is just water, the Arctic Ocean. There's no landmass there. But Greenland's close enough to the pole that it actually can accumulate a large ice sheet. Just for comparison, so here's Greenland here, here's Antarctica. The ice sheet on Greenland covers a surface area of about 1.7 million square kilometers, and it's got a total volume of 2.85 million cubic kilometers. Its maximum thickness is about a little over 3 kilometers. So think about 3 kilometers, it's like 1.5 miles of ice just sitting on top of the land, okay? And then Antarctica, for comparison, covers an area about 10 times greater area, so 12.37 million square kilometers, and a volume that's about 10 times larger too, so 25.7 million cubic kilometers of ice. And the peak thickness here is about 4 kilometers. One of the neat things that happens when you pile up glaciers on land like this is that you actually push down the middle of the continents. The weight of the ice sitting on top of it will cause the center of the continents to sink, and the continent will rise to the side. You know, just like if you had an inflatable, what do you call it, in the pool? You know, one of those inflatable lounges that we line in the pool, if you put a bowling ball in the middle, it would go down in the middle and up at the end, right? Same thing happens to the continents when you weigh it down with ice. So because of that, you actually get mountains along the edges of Greenland where you're pushed up on the side because of the weight of the glacier in the middle. It's kind of neat. So anyway, that's Greenland and Antarctica. Those are modern ice sheets. Other types of ways you can get ice ages or actually instigate glacial periods. Where does the Earth get its heat? From the sun, mostly from the sun. Some from the inside of the Earth, but mostly from the sun. And it turns out the amount of radiation that we get from the sun isn't constant. It varies with time. And in particular, it varies with what's known as the solar cycle, or the sunspot cycle. The sunspot cycle is an 11-year cycle of solar activity, where the sun goes from when you have periods of a high number of sunspots on the surface of the sun, and related to magnetic activity within the sun itself, you get more radiation coming from the sun. So we get more radiation here on Earth, and then we get a tiny uptick in temperatures. As you go back in time, you go to periods where you have less radiation from the sun. Okay, sorry, back in time would be that way. And again, this is over an 11-year cycle. You have fewer sunspots equals less radiation from the sun. And again, the peak to peak, this is like 1/10 of a degree Celsius or something, variation in temperature estimated. It's a tiny variation in terms of the amount of incoming radiation. But it's real and it's there. And this raises the question, it's interesting, if you look back at the historical period, there are a couple of periods, the historical record, there are a couple of periods in the 18th century, and then prior to that, there's the Dalton minimum and the Maunder minimum, these periods where you had, for some reason, the sunspot cycle missed a few beats, and you stopped having sunspots for an extended period of time. In the Maunder minimum, it was for something like these sunspot cycles disappeared, and you didn't really have sunspots for something like 100 years. And when you see that in the global climate record, temperatures drop a lot. Okay, and so it's entirely, and that's the Maunder minimum was this period where you'd have you know, the ice on the River Thames and London would freeze over, and you'd have winter ice skating festivals and that sort of thing. All these things that don't happen anymore. But when you read, you know, Charles Dickens' novels about winters in London, they were much harsher in the period that he was writing because they were coming out of this period of the Maunder minimum, which was associated again with lower global temperatures because of lower input from the sun. Okay, so that's the amount of incoming sunlight. Another way you can change, that you can cause global temperatures to drop and possibly instigate glacial period, is through not necessarily changing the amount of incoming radiation, but changing the distribution of that incoming radiation. Okay, so maybe it's not all showing up in the same place. Okay, and the way this works was discovered by this man here, Milutin Milankovic, who was a geophysicist. He was a Serbian geophysicist back in the early part of the 20th century. And what he discovered was that the Earth's orbit doesn't stay constant around the sun. The Earth's orbit changes around the sun with time in a regular, predictable way over periods of 100,000 years or shorter, actually, different things. And there are three different ways in which the Earth's orbit changes around the sun. One is that the eccentricity of the orbit changes. What that means is that when you look at the Earth and its orbit about the sun, it goes from being a pure circle, or almost a pure circle, to being an ellipse. Okay? And it does so over the course of 100,000 years. So it goes from being we're orbiting around the sun, and it's a nice circle, and then slowly it mutates and becomes an ellipse. And when it becomes an ellipse, you're further away at one end of the ellipse than you would be if you were circular, right? It's kind of like it gets stretched out and comes back. When you're in a pure circle, you've got nice even distribution of energy coming from the sun because it's the same distance from the sun at all times. If you stretch that out, you go through periods where you're further away from the sun and closer to the sun. Okay? That's what's known as the eccentricity. Then you also have obliquity and precession. Obliquity has to deal with how you know, the Earth, if you looked at the sun, the plane of the ecliptic of the sun, so if you're looking at the equator of the sun and the plane it makes, the Earth's pole isn't oriented 90 degrees to the plane. The Earth's pole is tilted 22 degrees or so from that plane. So there's an angle that the Earth's pole makes relative to the sun. Now, because of that, we have seasons. Okay, if the Earth's axis weren't tilted, you wouldn't have seasons. You'd always have the same length of day no matter where you were in the year. Okay, the tilt gives us seasonal variation. The amount of tilt, the more tilted you get, the more variation you have from winter to summer in a hemisphere. As it turns out, the Earth sort of wobbles like a top when it spins. So the tilt that it makes relative to the plane of the ecliptic changes with time. It changes over a period of roughly 41,000 years. Okay? And because of that, you get different degrees of seasonality over time. Okay? And then precession has to do with where the Earth's, you can think of the Earth's tilted, so if this is the North Pole, this is the South Pole. Okay? Right now, let's see, what do we want to do? Okay, you're the sun. Okay? So right now, the northern hemisphere is pointed at the sun. Okay? Does that mean we're in summer or winter here? Summer. Okay? And then I go and I'm orbiting the sun. Okay, and I'm orbiting the sun, and now I'm over here, and the northern hemisphere is pointed away from the sun, and what does that mean? We're in winter. Okay, so that's great, but gradually that changes. So instead of keeping an orientation like this, sometimes what happens is instead of pointing directly at you, at the sun, when I'm over here, I'm actually pointed like this. Okay, and now I'm in near the sun here, and I'm pointing directly at the sun, but I'm in a different part of my orbital path. Okay? And eventually you get to the point where the pole rotates, so instead of being pointing towards the sun over here, I'm actually pointing away from the sun when I'm over here. Okay? And then I'm pointing to the sun over here. So summer and winter essentially switch in terms of where we are in our orbit. Okay? And again, that changes when you take these three things, these are what are called Milankovitch cycles, the variations in the Earth's orbital parameters, and add them up, each one of them causes a change in the distribution, how much energy you're getting at a particular latitude at a particular time of year. Okay? So here's the variation. This is going back from today back 100,000 to 1,000, yeah, 1,000, this would be 1,000 years ago, so a million years ago. You can see this is the variation, and what they've done is this plot is essentially looking at how much sunlight would you get at one location, in this case 65 degrees north, at the summer solstice, so June 21st, 65 degrees north latitude. How much energy would you be getting from the sun? If you just look at variations due to precession, you can see it wobbles like that. Obliquity, it looks like that. Eccentricity looks like that. Those are the 100,000 years, so this is longer, so it takes longer to change. It's shorter, you get a much shorter wavelength. When you take these three and add them together, the total change in solar force, it gets pretty wild. And as it turns out, the peaks more or less align with periods. This is the glaciations here. Cold periods are down here, warm periods are up here, and the peaks correspond to peaks in the solar forcing.